Now, let's go to see a little bit of x86 architecture. Let's see the syntax, okay? So there is two types of syntax. One is called Intel, which is the one that I recommend, which basically, I'm going to explain you the format. You have a mnemonic, as you see in the move format before, is called a mnemonic. You have in the move operand, you have a destination and you have a source. In this case, you are moving NARI to EDX, right? And then you have opcodes and endianness. So normally in Intel, in Windows, is little endian. Most of the systems, all Windows on Linux are little endian. What little endian means? That means how the instructions in memory are going to be stored. For example, here you can see that the 90 is stored this way in memory. However, if you would have before this, if you would have big endian, not little endian, this 90 it would have been switched opposite, okay, like 00090. But at this point, just keep in mind that it's little endian and everything, and you will see it in the labs. Now, there is another syntax which is called AT&T. I never use it, to be honest, and I mean it's up to you, but I don't really recommend it. But basically what that means is that the instructions, as you can see in Intel, is destination and source. So in AT&T is switch. So instead of having destination and source, it has source and destination. Like in this case, instead of having move source to destination, you have move, in this case, the source is in the left side and the destination in the right side. But again, guys, we're gonna be working on Intel. I just want you to know there is an AT&T syntax, okay? Okay, let's see registers. What is a register? Registers are CPU memory addresses that can hold temporary information during execution, okay? In 32 bits, all of them are these guys, EAX, EBX, ECX, EDX. Some of them have a specific purpose, and some of them can be used randomly. You can use it in different scenarios. Let's see how you can use them, okay? So those, since it is 32 bits registers, that means those are 4 bytes of size, okay? But you can also have a lower register, which is only 2 bytes, 16 bits, where you remove the E, which is called extended, and then you have AX, BX, CX, meaning those are the 16-bit version of these 32 bits, guys. You can also go down for a 8-bit access, which is, instead of AX, which is 32, you can have AL, which is 8 bits of the lower bits, or AH of the higher bits, the remaining ones. In case you wanna just graph or get or store value at 8-bit level and not at 16 bits or 32 bits level, okay? Then you have a very, very important register, which is called EIP. This is instruction pointer, which basically means every time you are executing a program, AIP points to the instruction that is about to be executed, okay? Then you have eFlags. eFlags means in the CPU register, you have a status register. Let's see an example. A very common one is the 0 flag. It's like, for example, if you do an operation that the result is 0 or not 0, this flag is going to be set. For example, if the result is equal to 0, this 0 flag is going to be set to 1. That means that with that information, then the CPU can say, hey guys, you did a comparison. So tell me what is the value of the zero flag. If the zero flag is 0, that might mean it was a same value of two operands. Let's see that example in a second. You have another register which is called carry flag. This is set when the operation result is too large or too small, for multiplication, for example. And when you have the zero flag, this is very common. For example, as I was telling you, right? If you compare two values, when those two values are the same, the zero flag is set to 1. So you say, hey, register 1 is 10, register let's say, a EAX is 2000 and register EBX is 2000. You compare them, they are the same, then the zero flag is going to be 1. Then the CPU is going to say, hey, after the comparison, what is the zero flag? Is 1. Oh, that means EAX and EBX are the same. That's the way those flags are being used. Okay? Let's see basic instructions, guys. Move EAX, ECX. You see that previously. It's normal. This basically copy the contents from ECX into EAX. Okay? Move EAX 0x90. This copy the value of 090 into EAX. Move ECX, EDX. This copy the 4 bytes at the memory location pointed by EDX into ECX. Okay. Sub ECX, 10. This subtracts 16 bytes, which is the 10 hexadecimal, from ECX. XOR EAX, EAX. So this, eventually you will see what is XOR. Is very common operand. But basically, when you have the same values in XOR, that actually clears it becomes 0. So when you have EAX, in other words, bit by bit, you XOR them, you basically clears everything to 0. That's why this is a very common instruction when you see in assembly that you are clearing EAX. You are putting EAX to 0. Shift left EAX, 3. Shift left is shifting to the left bits to the values. I mean, we can get into more details lately, guys. You will see it, but a really nice way to explain it, shift left is multiplication. And basically what it's saying is multiply EAX by 8. Why 8? Because basically 3 means 2 to the power of 3. This value is the power. So 2 to the power of 3 is 8. Then this means multiply the value of EAX by 3. Shift right. Again, is shift to the right the bits of the value in the register. But also, again, a quick view of this is a division, which means divide EAX by the power of 2. 2 to the power of 2. So this guy is to the power of. But since this is 2, 2 to the power of 2 is 4. And then this means divide EAX by 4. Okay, this is another way for you to quickly see this instruction and see this is a multiplication or division. Conditional jumps, guys. So basically, you need to, the assembly code needs to decide if it needs to jump to another instruction. And normally, this is based on comparisons. And let's see some examples. The compare operand. The compare operand can tell, like, compare destination and source. Let's see an example. If the destination and source are the same, then the 0 flag is set to 1 and the carry flag is 0. Okay? If the destination is less than the source, then 0 flag is 0 and carry flag is 1. If the destination is bigger than source, 0 flag is 0 and carry flag is 0. Now, these status flags, how that reflects to the jumps. Let's see. Now, after these operands, it comes a JZ or JE operand, which is jump 0 or jump equal. This instruction is going to say jump equal, meaning if 0 flag is 1. So if you do this jump and the flag is 1, that means that the destination and source was the same because the 0 flags is 1, as you can see, guys, here. Okay? Clear? We'll see in the labs. Let's see another one. Jump not 0, or the same as jump not equal. Jump to the address if it is the comparison is not the same, meaning 0 flag is 0. This can be, depending on the context, if the destination is less than the source, or if the destination is greater than the source. Okay, these two, depending on the context, can be the decision to jump. For example, you can say, hey, let's check if these two guys are the same. You know what? They are not the same. They are different. Oh, they are different. Then 0 flag is not 1. Then I'm going to jump because these guys are not the same. Like comparing a password. Is this password is the same as the password that I know is in the database? No, it's not. Oh, then jump because it's not equal, and you jump to the exit function, for example. Test operand. This is another very common, guys, that you're going to be seeing a lot in assembly. Test is basically telling you that if this register, whatever it is here, is null. So, for example, normally you will see, sorry, aquí is test, not text. Test EAX, EAX, or text ECX, ECX always is the same register in this example, so that you can compare if it is null. Okay, and if it is null, you take some instructions. You will see an example in a second. And if this guy is null, then the flag is set. You know, the 0 flag is set if EAX is 0. Okay, let's see an example in a second. Okay, now jump greater. This is jump if the destination is greater than the source after a sign comparison. What is signing, guys? It's another term we're going to be seeing a lot. Sign meaning positives and negatives. You can have positive and negatives values, or you can have unsigned, which means all are positive values. So in this case, in a sign comparison, you can check if the destination is greater than the source, and if that's the case, then you jump. Okay, jump above. Jump if the destination is greater than the source and unsigned comparison. In this case, is when you have values which are all positives and you are comparing them, instead of values which are signed, basically positives or negatives. It's basically based on the format you take and you use these two different jumps. Jump above or equal. Jump if the destination is greater than or equal. That's why it's E. Or equal to source after an unsigned comparison. Jump less. Jump if the destination is less than the source after a signed comparison. Jump below. Jump if the destination is less than source after an unsigned comparison. So you can see we have for sign or unsigned, you have GL, JL, or JB. Okay, guys? Rep. This is my favorite. Rep instructions. You know, this is pretty cool because sometimes you see how in life is easy to compare, you know, something like in Python. If you're familiar with Python, you can see like a comparison pretty easy, but see how in assembly that works. For example, in the instruction will repeat until a certain value is set. Let's see. You can do a copy a string, you know, like in Python you can say a copy the hello to the variable b. You know, one single line, you say a equal to hello. You know, that's it. You're copying hello to the variable b. How that looks like in assembly. Let's see here. So you have ECX, which is a counter, which is how many times you're gonna repeat this instruction, rep. That's the first register, ECX. And see, ECX is tied to this command because this command, when it is executed, it needs ECX because ECX is gonna have the count of the how many times it's gonna repeat it. ECI is gonna have the source of the data and EDI the destination. Okay, so the rep is gonna say, I wanna another one. Red move SD. This D at the end, guys, means double word, meaning I wanna be copying double words. In other words, 4 bytes at a time. Okay, so every time I copy 4 bytes. How many times I copy 4 bytes? 7 times from ECI to EDI. So basically, you're copying cannot install service into EDI. And if you count 7 every 4, you will have 4, 4, 4. And if you count all these guys, is all the different size that you need to repeat in order to completely copy the string. So you can see, guys, how this guy in Python is A equal to cannot install service. This is how it looks in assembly. Okay. Let's see another example of a repi estos b. Okay. Again, this estos at the end is b. This b is not d. This for double word. B is for byte. You know, and now instead of double words is bytes. Let's see this example. So in this case, repi will need EDI, and EDI will contain the buffer to initialize, and ECX is going to be the size. AL, which is 8 bits, will contain the initialization value. Why we're going to use AL? Keep in mind the AL is 8 bits, if you remember, and that's because we're going to be using just byte size values. That's why we use AL. Okay, so then how that looks like? Okay, so you are gonna have ECX again with the count. In this case is 1FF in hexadecimal. Then you are gonna have EAX. In this case, if you remember, is gonna set it to 0. Okay, and that means AL is gonna be 0. And then in EDI, you're gonna have LEA is another instruction which loads in EDA an address. In this case, the address pointing to this guy. And then you have EDI, which is an address. You have a count, which is how many times. And you have the value EAX, meaning you're gonna be clearing EDI. Wherever EDI is pointing to, is gonna be cleared with zeros 1FF times, meaning 512 bytes. You know what this means, guys? This instruction is in C. Well, one of the instructions is called memset. Memset is one of the instructions which you use in order to clear a number of bytes in a specific address. So this is the way you do it. So this is in this case, guys. Let me just see this rep. You see at the end is D. Okay, we put B here as I was explaining, but in this case is D. What means this is that we're gonna do it again like here. We're gonna be moving 2 words at a time. If we wanna do it by bytes, we can just do B here, and we're gonna be just doing byte by byte. But in this case is to go faster, double words. Every 4 bytes are gonna be put zeros. Every 4 bytes in the loop. Okay. Let's see more instructions, guys. Repeat, compare, SB. This is compare byte by byte, but can be word or double word. I mean, as I said, guys, This B at the end is byte, W is for words, 2 bytes, D is for double words, right? At the end is just the size. EDI and ECI must have the buffers to compare, and ECX must have the length of the buffer, okay? The loop will decrement ECX in every loop and will stop when it is equal to 0, or as soon as no match is found. Okay, so this guy again is a comparison. It's like in Python you have a, if hola is equal to hola, what this guy is doing is it goes to h is equal to h, o equal to o, 1 byte by 1 byte comparing it. That's how it looks like in assembly. So again, you have in ECI one value, in EDI you have the other value to compare, ECX has the number of bytes to compare, and then repeat is gonna say do it in a loop ECX times, and then do it byte by byte. You go in ECI and EDI and you start comparing it. Okay, and as soon as there is difference between these two guys in every loop, it just exit. If not, it will go all the way to the ECX value. Okay, guys? So that's pretty much it.